All right, welcome back to linear algebra. In section 5.2, we're going to keep talking about the conditions under which a matrix for a linear operator is diagonal, when you can do that. So diagonalizing a linear operator. So let's start by recalling our work from section 5.1, just really the main definition that what we're going to call a linear operator. Everywhere here, V is a finite dimensional vector space over a field F. So T is a linear operator on it. It's called diagonalizable if there's an ordered basis for V in which the matrix in that basis is diagonal. Our main theorem is just kind of a semantic theorem that an operator is diagonalizable if there's a basis of eigenvectors. Eigenvectors being vectors that are sent to scalar multiples of themselves under the function T. So the main question is, well, when do the eigenvectors for T form a basis? When is T diagonalizable? Okay, so here's kind of a first crack at answering that question, theorem 5.5. If you take a linear operator, and let's suppose that it has k distinct eigenvalues, okay? So lambda 1 through lambda k are the distinct eigenvalues. Then if for each one of those i's, if we denote by vi an eigenvector that corresponds to the eigenvalue lambda I, then those eigenvectors form a linearly independent set, okay? Or said briefly, the eigenvectors that correspond to distinct eigenvalues are linearly independent. Okay, we're going to prove this by induction on the number of eigenvalues, the number k. So first of all, if k is equal to 1, T has exactly one eigenvalue, then this set has one eigenvector. Eigenvectors are never zero, and so a set with a single non-zero vector in it is linearly independent. So there's our base case. Okay, so for the induction hypothesis, let's suppose that for some k at least 1, if this operator T has k distinct eigenvalues, let's call the corresponding eigenvectors V sub I, then that set will be linearly independent. That's our induction hypothesis. Okay, so it's true whenever you have k distinct eigenvalues. And now let's suppose that we have a linear operator that has k plus 1 distinct eigenvalues. Okay, so I'm writing lambda 1 to lambda k plus 1. And same notation, corresponding eigenvectors V sub I. It's k plus 1 of them. I want to show that the set v1 to vk plus 1 is linearly independent. Okay, so suppose we have some scalars that multiplied by those things sum to give 0, typical linearly independent argument. Suppose a linear combination of them is equal to 0. I want to prove that all those scalars, alpha 1 to alpha k plus 1, are 0. So what I'm going to do is I'm going to apply the operator t minus lambda k plus 1, the k plus first eigenvalue, t minus it times the identity matrix, or sorry, the identity operator, to that sum. So if you apply that thing to one of these terms, let me kind of write in the details here. So if I apply that thing, I'm going to kind of save some space here. So if I apply that to say an alpha I vi, well, I push it through linearly, so I would get alpha I times t of vi. Well, t of vi is called lambda I vi. And then, well, the other operator is just the identity matrix. So I would end up getting alpha I times the quantity lambda I vi lambda k plus 1 vi, right? Because the identity operator sends vi to itself. And if you factor the vi out on the right-hand side of that thing, you get alpha I times lambda I minus lambda k plus 1 vi. Okay, so that's just applying that thing to each one of those terms. Well, it's a linear operator, so you push it through the sum. And so what do you get? Here's what you get when I is 1. You get alpha 1 times that quantity times v1 when I is 2, and so on, up to I equals k. But why no k plus 1? Well, if I is equal to k plus 1, lambda k plus 1 minus itself is 0. So the last term vanishes. Okay, so we get that new sum. But now the v1 to vk by the induction hypothesis, that's a linearly independent set. So those coefficients, alpha I, or I guess I called them alpha j, sorry, alpha j times those quantities, those are all equal to 0 for j equal 1 to k because of the linearly independence. right? But we're saying those were distinct eigenvalues. So for j between 1 and k, lambda j never equals lambda k plus 1. So the terms that are parenthesized, if I underline them, these things are never 0. But if the product is 0, it must be alpha j's fault, quote unquote. So we must have the alphas up to alpha k. Those things all have to be 0. Well, then returning to that original sum, if all of the first coefficients are 0, it implies that that last coefficient, alpha k plus 1, has to be 0 as well. Okay, so that means that the alpha k plus 1 is 0. So we've shown that all the coefficients are 0. So that's linearly independent. That completes the proof. Nice. Here's a little corollary of that. If the dimension of your space is n, and this operator has n distinct eigenvalues, lambda 1 to lambda n, then it has to be diagonalizable. Why is that true? Well, because if you take an eigenvector for each one of those eigenvalues, we just proved that that set's linearly independent by the theorem, but it's got the right number. It's a linearly independent set with dimension of v elements in it, so it has to be a basis. And if you have a basis of eigenvectors, then you are diagonalizable by theorem 5.1. So there's one answer to the question. It's not the only answer. It's not an if and only if, but if you have a linear operator and it happens to have n, and the dimension of v is n, and it has n distinct eigenvalues, then it's always diagonalizable. The converse of that is false. So just because an operator is diagonalizable doesn't mean that it will have n distinct eigenvalues. The kind of examples that come to mind first is, say, if you take the 0 operator. The 0 operator is diagonalizable. But it only has one eigenvalue. Another example of the sort of opposite extreme is if you take T to be the identity map. The identity map is diagonalizable. I'm going to do that to be lazy, but it only has one eigenvalue as well. All right, so just because you're diagonalizable doesn't mean you have kind of a full suite of eigenvalues, but if you do, if you have n distinct eigenvalues, the dimension of v is n, you're always diagonalizable. Let's look at an example. Here I've got a 2x2 matrix A. So again, if it's not clear already, whenever I'm switching to matrices, well, I'm just talking about the linear transformation being the left multiplication by that matrix. Okay, so if we compute the characteristic polynomial of that thing, you take the determinant of A minus T times I, you can check the computation and simplify that polynomial. It's T minus 1 times T minus 3. So it has two distinct eigenvalues. Sorry about that. That's should say eigenvalues, not vectors. It has two distinct eigenvalues. Can you see what they are from the characteristic polynomial? They're lambda equaling 1 and lambda equaling 3. So two distinct eigenvalues. 2 is the dimension of F2. So that thing is diagonalizable by the corollary. There's a little terminology. Polynomials, polynomial f of t with coefficients in the field f, we say that it splits over f if there are some scalars, a1 to an and c, such that f is written as a linear a product of linear factors. So c is just sort of the leading coefficient, if you like. So if you can factor your polynomial into linear factors, each linear factor is also a polynomial over capital F, then we say that the polynomial splits over F, and it splits up into linear factors, if you like. Like so, for example, if we look at the polynomial t squared minus 1, it splits over R, because t squared minus 1 factors over R into t minus 1 times t plus 1, and minus 1 and 1 are both real numbers. Okay, the polynomial g I've got written down here, it splits over c. It factors into t plus I times t minus I over the field of complex numbers, so it splits over c. But I and minus I are not real numbers, so that polynomial doesn't split over R. It doesn't factor over R into linear factors. So splitting over a field means factoring into linear factors over that field. Okay, so the next result, theorem 5.6, if you take a diagonalizable operator T, then its characteristic polynomial f of T will split. So if you're diagonalizable, your characteristic polynomial splits over f. How are we going to prove that? Well, if T is diagonalizable, then there's a basis of eigenvectors. Okay, if there's a basis of eigenvectors, say v1 to vn, the matrix for T in that basis is diagonal. The diagonal entries are the eigenvalues. All right, so if you're diagonalizable, you have a diagonal matrix. The diagonal entries are the eigenvalues. We proved before that characteristic polynomials don't depend on what basis you use. So if we use this basis, you can easily see that the characteristic polynomial is going to be minus 1 to the n times the product of t minus lambda I, where I goes from 1 to n being the dimension of the space V. So the polynomial splits. Okay, so if you're diagonalizable, your characteristic polynomial splits. Here's just some terminology, some more terminology about polynomials, that if you're a diagonalizable operator and you don't have dimension of V distinct zeros, distinct eigenvalues, then some zero has to have multiplicity greater than 1. So what's the multiplicity of a zero? Remember, if you take a polynomial, the multiplicity of one of its zeros, a zero is a number that makes the polynomial equal to 0 when you plug it in. Its multiplicity is the exponent on that factor. So it's the largest integer such that t minus that 0 to the m, the largest integer m, such that t minus that 0 to the m is a factor. It's called the multiplicity of the zero. So if we look at this example down here, my f of t, it's got 3 zeros. So the zeros are, I'm going to call them lambdas, lambda equaling 1, 3, and 6. And what are their multiplicities? Well, it's the exponents. The multiplicity of the 0, lambda equal 1 is 1 because of that exponent. The multiplicity of the 0, 3 is 5. It occurs to the 5th power. The multiplicity of the 0, 6 is 2. Okay, so it's just the exponents. The multiplicity of the 0 is sort of how many times that factor shows up. So my remark above is that if you have a diagonalizable operator, but it has fewer than dim v distinct zeros, then in its characteristic polynomial, at least one of those zeros has to have multiplicity greater than 1. Okay, if you think about the argument that we just gave above, the same eigenvalue has to occur at least twice on the diagonal of that matrix in the basis that diagonalizes the operator. Let's look at a quick example to end this lecture. A differentiation operator again. In the standard basis, its matrix, I'm just going to shortly denote it by A here. You could stop the video and double check that I've got that matrix correct. So the derivative, the matrix of the differentiation operator in the standard bases. So if we look at its characteristic polynomial, that is, we look at A minus T times the 3 by 3 identity matrix, you get this 3 by 3 matrix, which is upper triangular. So its determinant is easy to take. So the characteristic polynomial is just negative 1 to the 3, if you like, but it's easier to write negative 1 times T cubed. That splits over R. Okay, that's 3 linear factors. It's t minus 0 times t minus 0 times t minus 0, if you like, to emphasize why it splits. It's got 3 linear factors, all of whose zeros are in R. Okay, but if we look at the null space, the one and only eigenvalue is 0. So if we look at the null space of A minus lambda I, that is just the null space of A, because lambda is 0. Well, it's those vectors x1, x2, and x3 in R3. Just look at the matrix A. It would have to be the case that x2 is 0 because of the first row. 2 times x3 is 0 because of the second row. x1 is a free variable. All right, so that null space is therefore the span, if you choose x1 to be 1, of the vector 1, 0, 0. So there's a basis. There are no other eigenvalues. It only has one eigenvalue, lambda equals 0. So there are no other eigenvectors. And in particular, there are no other linearly independent eigenvectors. So there's no basis of eigenvectors. Okay, so this matrix is not diagonalizable. So that operator is not diagonalizable. Okay, so why mention this? Well, it's just kind of a nice example that the converse of theorem 5.6 is false. Theorem 5.6 says that if you're diagonalizable, your characteristic polynomial splits. Well, this example is showing us that that's not going to be an if and only if theorem. I showed you an operator differentiation on degree 2 polynomials. Its characteristic polynomial splits, but the operator is not diagonalizable. Right? It's a three-dimensional vector space, but there's only one eigenvalue, and the eigenvectors that go with that eigenvalue just form a one-dimensional subspace. So it's not diagonalizable. Okay, we're going to keep this one shorter and call it quits for there. So thanks for listening.